So we left off talking about the projection vector and decomposing a vector into two orthogonal vectors, one of which is the projection vector. One place where we use projection vectors is in physics. When we have a force applied that's not in the same direction that the motion is going to move, we can use the projection vector to figure out how much force is working on the object. And I don't have an example here, but I think I'm going to add one in here. I'll just put it on the back of this piece of paper. So let me give you an example. Let's say we have just like 100 pound of something on a ramp. So this weighs 100 pounds. So our force is going straight down, towards the center of the earth. That's the direction the force is being applied. So, working with gravity. So this force vector would be negative 100J. All the direction is vertical and heading down. And of course, we're going to ignore friction here. Well, not of course, but I'm telling you that. We're going to ignore friction. And of course, then this object would slide down the ramp, right? It's moving this way. So our question is, or where we can apply the projection vector is, how much force is actually, heading down the ramp here. We can think of this as, well, how much force would I need to apply here so that this object does not move? So let me write that down. So what force is required? So let's just call it a box, doesn't slide down the ramp. Because the force is not going this way, right? If the force was going this way, we would need to apply 100 pounds this way so that the resultant force would be 0, then the object wouldn't move. We want the resultant force to be 0 as well here, but because the force is not in the same direction as the ramp, it's not 100 pounds of force required. It's going to be less than that. So the answer is it's the length of the projection vector. So if we project this over here, the length of this vector, which is the projection vector, is the force required. And we're projecting F onto, let's call this, of course, this will be the projection vector. I don't want to put V here. Let's just call this vector V. Right, we're going to project the force vector onto vector V. So the magnitude of that is the force required. So to get the answer, we can just, of course we don't have a V given, right? We can just create V using the angle of the incline. So let's just say this is, so from the horizontal, maybe this is 20 degrees. So let V equal, just use a unit vector. So cosine 20 degrees I plus sine 20 degrees J. Any vector going in this direction will work. It doesn't have to, have any particular length. And so we'll just use the unit vector and project onto that. So now let's find the projection vector. Oops, oh, that's okay. So projecting F onto V. Of course, that's F dot V the magnitude of v squared, and the fact that we used a unit vector here makes this real simple, right? So even if this weren't a unit vector, you're going to create, or divide by that magnitude so we get the right size vector times v. Okay, so f, remember f is negative 100j. So the horizontal component of f is 0, so 0 times cosine 20 is just 0, plus negative 100 times sine 20. Maybe I should have used 30 degrees there, then I could have done that without a calculator, huh? That's okay. And then of course we got 1 squared, so this is just 1 down here, and then times our vector. So I'll have to use a calculator here. Make sure I'm in degrees. Okay, so sine of 20 degrees, and then I'm taking that times 100. Well, negative 100. So negative 34.2 times cosine 20 degrees I plus sine 20 degrees j. And since this is a unit vector, we want the magnitude, of this vector, but because this is a unit vector, this is the magnitude in an absolute value. So the magnitude, make sure I'm on the screen here, the magnitude of the projection vector is 34.2 pounds. That's our force required. So notice a lot less force required to keep it from rolling down the ramp, because the force is being applied into the ramp. And so this vector that we found, if we add it, and remember if we could find this vector as well now, if we subtract, I'm not going to do it, but the sum of this vector and this vector would balance out this vector, and that's why the object doesn't move. Okay, so there's one application of a projection vector, and then we're going to also look at work. We can use projection vectors there as well. So when a force is applied in the same direction as the motion, we don't need to use vectors. You probably learned this like in 9th grade science or something. Work is equal to force times distance. So you just take the force times the distance the object moves, and that gives us the work. So here's a real simple problem. You have a 10-pound package, that's the force, and it moves vertically through a distance of 4 feet, that's our distance. How much work is done? Work would be 10 pounds times 4 feet, so 40 pound times feet is foot-pounds. That's the unit of work there. So that's real straightforward. But in reality, often the force is not applied in the same direction as the motion. And if that's the case, then we need to use vectors and a projection vector. So, there's the page, there it is. I'm out of order because of the extra example I did. All right, so using vectors now, it says the work done by a force moving an object from point A to point B, doesn't have to be in the same direction, would be equal to the force vector times this is weird. I wonder, hold on a second. This isn't what I don't know why I wrote this. I mean, this is correct, but I wanted to end with this step. So let's look at this one. I should have another step in here. Let me put it over here. Work equals, all right, let me draw a picture and I'll explain what I'm doing. So we have the object moves from A to B. the force, say, is applied this direction, then this projection vector is here. The projection of F onto AB, the magnitude of that is the force required. And the magnitude we showed back in, let me see, we already talked about this, but just to remind you. Oh, shoot, pages are out of order. Here we go. Right, we talked about how the length of this is equal to the first component of U here, well that's F here, so that is the magnitude of F times the cosine of theta, where theta here is the angle between the force and the direction of the motion. So the work is equal to the magnitude of the projection vector times, so this is our force, and then times the magnitude of AB, that's our distance. I don't know why I didn't have that step in there. So from here, we can use, now again, we have to refer back to remember what we've done. If I can find it now. Oh, I already did it, sorry. This is equal to this. So if you replace this times this, you get this step, and then this is just the definition of the dot product. So we can use this formula or this formula. We're going to use this formula in our example. But if you have the vector in component form, right, then you can just take the dot product of the force vector times the dot product of vector AB. On the screen. Okay, so we're going to use this formula in our example. So this example is pretty straightforward. It says a wagon is pulled along level ground by exerting a force of 40 pounds on a handle that makes an angle of 36 with the horizontal. So we have a wagon, the handle is the direction the force is moving, but of course the wagon moves this way, right, from A to B. And this angle is 36 degrees. So the magnitude of F, see we're not given F in vector form, but we're given its magnitude, 40 pounds. And the magnitude of AB is, that's how far the object moves, that's 200 feet. So work equals the magnitude of F times the magnitude of AB times the cosine of theta. So 40 times 200 times cosine of 36 degrees. 40 times 200 times cosine of 36. So that's approximately 6,472, and then this would be foot-pounds. So we used English units in both of these problems, but often force is given in newtons, in SI units, and then distance in meters or centimeters. So then it would be Newton meters or Newton centimeters units for work. All right, so you can let me know if you have any questions about that.